It is 5 past, so as I say, congratulations for having turned up. We seem to have less than half of the cohort here, but of course, you know, we'll do our best. Now, I was saying to a couple of students I saw on the way up, you know, like help me find chemistry by following them, was that the last lecture was probably mathematically the most demanding of the whole course, and also conceptually demanding, because you've only previously been introduced to scalar potentials, and you know, we've been over this a couple of times. The scalar potential will only be used if we've got a field which has got a zero curl, and of course the whole if you like, the definition of the magnetic field is that it has a finite curl determined by the currents. Now, the point we got to was that we were able, although the vector potential looks quite complicated, it reduces when we did again, this is, remember, we had to choose the gauge that del dot A is equal to 0 in order to make this simple reduction. You see that these equations for each separate component of the vector potential are mathematically identical to Poisson's equation. Now, all we've got to do to solve for the components of the vector potential is to use what we know about electrostatics, the kind of solutions that we've done, and this will give us, of course, physically it's different. Here we've got a charge density determining an electric potential. Here we've got an x component of the current density determining the x component of the vector potential, with similar equations for the y and the z components. And of course, rather than constantly write out all the components, we have got a compact notation for writing them, applying del squared to the vector A, the vector potential A, is equal to minus mu naught times the current density J. And of course, the final step in the calculation is completely different. Although we can determine the electric potential from the charge distribution, if we then want the physically real electric field, we take the negative gradient. However, when we have determined the vector potential from the charge density, we then have to take the curl of the vector potential in order to determine the physically real magnetic field. Now, again, I'm going to, in the first half of the lecture, this is going to be very much a lecture of 2 halves. We'll do really the Biot-Savart law in the second half. In the first half, I'm going to demonstrate how this machine, if you like, for calculating works in a very simple case. So the particularly simple case is, of course, the long current carrying wire, and one that we've already done by Ampere's law. It's such a high symmetry, we can solve directly with Ampere's law, but it's nice to see with such a conceptually simple problem how the vector potential actually works. And so here we've got it again. There's a wire carrying a current I. It's an infinitely long cylindrical wire, and I want to know the magnetic field at some point P at a distance r, given as an r prime here, from the wire. Now, again, you see, this is conceptually very easy, because we know, let's just go back to that first view graph, that, put it inconveniently over here, let's get it there. Well, we know in this case that there's no y component or x component to the current density. The current is here given as the vector j. Sorry, I shouldn't just say the vector j is jz. The current density is no component in the xy plane, and it's got some finite density along the z-axis. So immediately, well, of course, we're not going to bother to do these two integrals, because jx is 0 and jy is 0. So obviously, the x and y components of the vector potential are immediately 0. We've only got to determine a single component, the z component. So this is, again, I wasn't sure about how the setup would be here, and again, I've not got many blackboards, so I'm pleased I have decided to do it this way. I'm going to go through the view graphs, and I would say again, for the point of view of note-taking, again, this is conceptually new, using the vector potential. The notes are identical to what's on the VLE. It's up to you whether you want to take notes for your own benefit as you go along, but I would say it's probably better simply to follow the calculation and use the notes on the VLE afterwards. So clearly, well, just our definition, again, we've got this lovely simple problem. If I multiply the current density in amps per square metre by the cross-sectional area of the wire, I'm going to get the total current in the wire. So that's a very easy kick-off step. Equation 6.1, because normally when we're dealing with magnetic fields around current carrying wires, we use I as a variable, and J is obviously the variable we need in the calculation. So as I said, because the current has got 0 components in X and Y, we can immediately say that exactly here, because this is 0, we have no components in that plane. So again, equation 6.2 is just restating what we've said already at the beginning. Now, this is the cunning part, if you like. To find JZ, we can use because we're mapping these equations across, because we've got this one-to-one mapping, all we've got to do is replace our in this case AZ, that's the only non-zero component, because this is the only non-zero component here, with phi. We replace our 1 over epsilon naught with mu naught. These constants out front, instead of 1 over 4 pi epsilon naught, become mu naught over 4 pi. And we replace our integral over all spaces occupied by charge with the integral over all spaces occupied by currents. So if we can solve this problem, we can certainly solve the corresponding magnetostatic problem. And you've done this last year, that the electric, and again, at your level now, you can solve this in a couple of lines. You know, so there's my current. You see, we're mapping onto now a charged wire. Be careful about the thinking. This isn't the magnetostatic problem. This is the electrostatic problem. Well, of course, because of the symmetry, I'd surround my charged wire with a Gaussian cylinder. And the same old argument that we've had, if I've got cylindrical symmetry, if I've got this, if this was charged, well, clearly there's no reason for the field to be different in any direction. So in other words, when we do our integral of E dot n dA over the surface, and again, we can use the simple version of Gauss's flux law of electrostatics that Kieran gave. That's the total charge inside over epsilon naught. Likewise, there is absolutely no reason for the magnitude of the vector at a fixed distance to be different in any direction. So we can simply say that this, it's, you know, our usual argument, they're parallel, this just becomes the magnitude of E, E's constant, that comes out of the integral. And if we, therefore, let's call it the radial component, because it points radially out from the wire, the radial component times the surface area of the cylinder, which is 2 pi RL, well, the total charge, Kieran did this as lambda as the charge per unit length. Well, obviously, the total charge is the charge per unit length times the length over epsilon naught. And straight away, we know that the electric field, therefore, the L's cancel, is equal to lambda over 2 pi epsilon naught R. So that's a calculation that you did last year. And of course, we know that the corresponding potential is going to be minus lambda over 2 pi epsilon naught times the logarithm of R. Obviously, if we integrate 1 over R, remember E is equal, this is now just a rate, is only varying radially, so this is equal to minus d by dr of phi. So we know perfectly well that if we, remember, I've got a minus sign in here which comes from this negative gradient. Clearly, if I differentiate this, I get this, and if I integrate this, I get this. So this is a problem we've solved. Now the clever, subtle point, although we've not solved it, we've used this, we've solved it via Gauss's flux law of electrostatics, but we know that although you haven't done the second order partial differentiations, you should be quite clear from the work we did in lecture 2 that that's equivalent to solving Poisson's equation. So if I solve for phi via Poisson's equation, I've obviously got to get this answer. It's the same problem. So I don't need to redo it via a second order partial differential equation. I've automatically, because we know Gauss's flux law of electrostatics, using Gauss's theorem is equivalent to Poisson's equation, I know the answer to this problem. And that's exactly what is stated here. I know how to do that problem from basic electrostatics, and these are the answers for the electric field and the electric potential. Now that must be the solution of this equation. Again, we always with these things, be careful with mappings, make sure you get it all right. We've now got to like an equivalent problem. Let's say rather than an infinitesimal, we've got a little thin, which of course would be more like reality, charged wire. Well, if I want to map the solutions over, of course the charge density in coulombs per cubic metre has to be multiplied by pi a squared, where a is the radius of the wire, in order to get the charge density per unit length. That's, again, a relatively trivial change. This is just saying, well, this is multiplication by the cross-sectional area of the wire. Oh, thank you very much. Of course there shouldn't. No, when I differentiate log r, I get 1 over r. Thanks. That was a, again, deliberate mistake. Check you were on the ball after the long trek up to chemistry. So, no, it wasn't actually, but there we go. So, yes, thanks for that. Of course, that was quite right. So all I've got to do is map across to get this AZ. This is the solution of the same equation. Is going to be equal to this. This is my equivalent here of my rho. Remember the epsilon naught becomes a mu naught in the numerator, but functionally AZ has got to be exactly the same. And then again, because when we're analysing the fields around fine wires, we usually write pi a squared jz is equal to I, we can re-express it in this way. So now we've found that the vector potential in this case is actually rather simple. No x component, no y component, and a z component, which give or take the constant, is just the logarithm of the radius from the wire. So now at this point, of course, we've solved for the vector potential. We now have a completely different step. To get the magnetic field from the vector potential, I take its curl. And to take the curl of this, well, this is the step here. There are only 2 of the 6 derivatives that are not 0. So this is why I sort of pop these up at the beginning, just to make sure the whole thing's convincing. Well, AY is equal to 0. Yep. Now that's it is this vector here. AX is equal to 0. We don't have to bother about that, and immediately BZ, the Z component of the magnetic field, is 0. We'd be worried if it was otherwise, because we know with a current going, if that's the Z direction, we know already that the magnetic field lines are circulating in the XY plane. So this is precisely now, this comes out of the machine, that's automatically 0. Likewise, thank you very much to being pointed out here, this is an AX, this is of course 0, and similarly AY is 0. So BX is just this one, and BY is just this one. So all we've got to do is perform these 2 differentiations, d by dy. Again, I've taken the mu naught I out front, got the signs into it, and all I've got to do is take d by dy and d by dx of log r. And again, you know, it's the kind of thing you were doing with Peter Main in partial differentiation last year. Let's take that y derivative of the logarithm of r squared plus x. Of course, r squared is x squared plus y squared. We're in the xy plane. and r is therefore the square root of x squared plus y squared. Indeed, we kind of did that in Maths 1 when we first looked at polars. So when I differentiate the log, I get 1 over x, of course with respect to the y differentiation, this is just a constant. I get 1 over x squared plus y squared. It's, if you like, a double chain rule. I then have to differentiate x squared plus y squared to the half, bring down the half, decrease the power by 1, but then it's still a function of a function, so I have to multiply by the derivative of what's in the brackets, which is 2y. The halves cancel, so that goes, take the y to the front here, that goes, and I've got x squared plus y squared. Sorry, this is to the half, of course. Second deliberate mistake. So this is x squared plus y squared to the minus a half times x squared plus y squared to the minus half, x squared plus y squared to the minus 1. Pop it into the numerator, and I've got y. Again, re-express my x squared plus y squared as r squared. I've got y over r squared. So again, that's it's in the end a simple chain rule differentiation, but I wanted you, to be convinced that equation 6.5 and 6.6 and 6.7, for the z component, necessarily follow. So now we've got our magnetic field. Now, to make this a little bit clearer, I've rewritten it. Well, the next step, again, I want the whole thing to be completely convincing. I wrote the next step on this board. Of course, I've taken out I've got an r squared there, yes, I've got a minus y over r squared for the x component. I've taken this out so that the derivation, I think, becomes a bit clearer. The y component, I've got an x over r squared, and the z component, I've got 0. Now, if I want the modulus of this vector here, well, if I dot that with itself, I get y squared over r squared plus x squared over r squared, which is y squared plus x squared over r squared, which is 1. I think that's what makes it clearer. So clearly, I've got a magnetic field which has magnitude mu naught I over 2 pi r and a x component which is going in the negative y direction, and a y component which is going in the positive x direction. And of course, what I'm describing in terms of the direction is a field circulating in the xy plane. So I've solved this now from first principles using the vector potential. And clearly, I can say that we get the same result as before. We'd be very worried if we didn't. We've already solved this in lecture 4 by Ampere's law, that I have a B field that circles around the wire. That came out of the calculation. The x component is always going as minus y. The y component's going as minus x. And with magnitude mu naught I over 2 pi r. And again, usually written by lumping that together and emphasising it's linearly proportional to the current and inversely proportional to the distance from the wire. Now, that is like with the proverbial using a hammer to crack a walnut, because we could solve that almost by symmetry in a few minutes. We kind of went, well, there's my current carrying wire, the field lines are circular, and if I do B dot ds is mu naught I, again, at the level you're at now, this is a very, very quick calculation. Well, that one's the magnitude of B times 2 pi r, and I get it almost as a one-liner. You can do it almost immediately. But the point is, I can only apply Ampere's law in this very high symmetry case. This machine that we've got now works for absolutely any case whatsoever. And in particular, you have got, again, we'll come to this in a bit, we might want to solve for the magnetic field of some rather complicated circuit. Some engineer might be doing a problem and the only way they can get the wires around all the bits is to sort of, loop them around. This new machine Well, for each little current element, I find it's x, y, and z components of the current element. Then it's a simple integration to get the x, y, and z components from, well, it's simple, might be quite tough solving this second order partial differentiation, but of course we can leave that to the engineers and say, you know, we're doing the high symmetry problem. However, this is, if you like, gives you a complete machine for solving for the magnetic field in any circumstances. And also, again, this is the next page. We are in a minute going to say a lecture of two very distinct halves. I'd just like to say something about the role of A. I'm coming to how we get B directly from the currents. And it sort of begs the question, well, if I can get B directly from the currents, why the hell have I bothered with all this intermediate stuff with the vector potential? And there's three very powerful reasons why. First of all, when you do the Biot-Savart law, and you've already done it with Kieran, you have got, and it's rather nasty, I'll come to this in a minute, you've got a cross product under an integral sign. And this is actually mathematically a really nasty brute to deal with. Again, in almost all circumstances where you have a non-high symmetry problem, to have a cross product under an integral sign gives you an extremely difficult direct integral. So mathematically, if you really want to solve a problem of anything other than high symmetry, the integrals for B are usually much more complicated than the integrals for A. So there's a technical reason for going via the vector potential. It's easier mathematically. Second reason is that it's actually, well, you know, like you can apply everything you've learned about electrostatics, and your EM1 course was probably, you know, almost a half electrostatics. You immediately just map it over. That's precisely what we did. Oh, well, last year you studied field of a charged wire in cylindrical symmetry and got this result for the electric potential of a charged line charge. But you can immediately use that now. And use the knowledge. So if we already know the solutions for, you know, for the electrostatic problem, we don't even have to do the integrals for A at all. We know the answers. Second, but the third reason, be coming back to this in when we do the unification theory, when you go to advanced theory, this combination phi AX, AY, AZ transforms like a 4 vector, and this is precisely how special relativity was discovered. And this is, if you like, the time component, the x component, the y component and the z component in space-time of what's called a 4 vector. We'll be coming to that in a couple of weeks' time. And it transforms under, again, you'll have done this with John last year in special relativity without seeing where it came from 19th century physics. It obeys a Lorentz transform of time, x, y, and z. So we can construct a Lorentz invariant combination out of phi, AX, AY, and AZ. It's a 4 vector. Now, you'll see in the notes to be discussed in EM3, we used to have a third. At one point it was called EM theory in the 4th year. At one point it was called EM3. It was a 3rd year course. And I taught EM3 when I first came here. Unfortunately, there are many things, you know, the projects have been expanded since. There's no longer advanced electromagnetism courses in this department. So when you come to this aspect, I won't be able to cover it all in this course, but there are some so-called advanced topic talks on the VLE. So there are very good reasons for going via the vector potential. It's not just something I've made up to re-solve problems. It's got a much more advanced application. And of course, particularly too, that you will come back to it in 3rd year quantum mechanics. The vector potential plays a role in advanced quantum mechanics as well. So again, it will be useful to you in the 3rd year because it's in your next year quantum mechanics. Now, what people discovered, and go back to the a view graph shuffling monster, is that you can do, just like in this problem, because it was like a very high symmetry, we kind of solved for the electric field directly and went backwards and got the potential. And there is a possible way of solving for the magnetic field directly. In other words, we combine the two steps. Now, this was our answer for the vector potential. And we know that that's just generally true. We also know that this is generally true, that the magnetic field here is equal to the curl. I should say again, this 2, this refers to the point at which the element of current density exists, and this 1 refers to the point where we're calculating the magnetic field. And that's precisely what's shown in figure 17 of the course handout. So, and this circuit is drawn like in a deliberately ridiculous way to emphasize that you can do it for any arbitrary element. So we've got here a little circuit element of current going round, and again you'll note this is I ds2, but we can also represent that, as mentioned this right at the start of the course, as J dv2. That was what was shown in figure 16 of the course handout. We've used that already, that this, we put the vector nature into the J, and this one again is my amps per square metre, this is in metres cubed, this therefore is in amp metres, and obviously that's in amp metres because that's the distance. I kind of swap the vector nature over, and there's some little current element here produces a magnetic field at this point 1. So this is what that, and R12 is the vector, again this was copied from a book, from point 2 to point 1, and I can also express that as R12 magnitude times unit vector from point 1 to 1, 2. So there's a lot of just tricking around with the symbols, but that's the relatively trivial part of it. Now, and this is definitely the non-trivial part, I can therefore always express my magnetic field directly as mu0 over 4 pi times the curl of this integral. Now, even Feynman ducks out of the next step in his lectures, and it is a non-trivial proof. Now, I used, when I was, and I emailed you about that, how important, it is to get really the feeling that you're confident at the curl of any vector field. Oops. And that we proved that the divergence of the curl of any vector field is naught, and this was equal to, not naught at all, equal to the gradient of the divergence minus the Laplacian, because we need that in the unification theory. Now this maths we don't need at all. This is the only place it would crop up, and it's difficult and long-winded. So I just thought, well, it is of course, I'd love in the spirit of this course to derive everything from first principles, but I don't want to use the whole of the rest of the lecture on this step. It's definitely not trivial to prove that. Again, this is the unit vector, which is of course the vector divided by its magnitude, and that to that is absolutely non-trivial. However, it is true. And if you note that we can use this JdV is IDS, we can re-express that in terms of a scalar current, which will come out the front, times this cross product of the displacement vector around the circuit times the unit vector from the circuit element to the point in question, divided by the square of the distance between them. So now I'm going to kind of, because now in the front row, you weren't warned. This is another audience participation lecture. There's going to, unlike those wonderful Indian gods with 6 arms, which I can't hold about 5. You see here my teaching aids, no expense spared. I've got 2 meter rulers and 3 short rulers to do the demonstration. So so this is now, if you like, lecture 6. It is non-trivial to prove, but it's true that that the magnetic field at point 1, which we know is equal to the, well, we can always take this fundamental constant out the front. That's just a fundamental scalar. That's not going to change. That this is where we sort of got to, that we would have to take the curl of the integral of the current element at point 2 dv2 over R12. And again, it's just a note, but people sometimes get confused. Of course, this has dimensions. This is an operator with dimensions L to the minus 1. Here we've got an L to the minus 1 also, because we've got an R12 in the denominator, and it comes out here. I've circled it. This R1 squared is true, but it's not, as I say, trivial to prove that this is, maybe let's call this 6-1, is equivalent to, and then this is the way the Biot-Savart law is normally written. So I don't want to obscure the board, so I'll just write it lower down here, is equal to, again, of course, this constant, we don't have to worry about carrying that, but proving that this comes down to being the scalar current times ds2 cross product with the unit vector from point 1 to point 2 divided by the square of the distance between them, which is the Biot-Savart law. As I say, it's non-trivial, but it's true. So we've introduced the vector potential, if you like, for future reference. In this course, I'm not going to set you, of course, to solve some ludicrously complicated low symmetry circuit. We'll be sticking to, you'll be surprised to hear, circuits where it goes round in a perfect circle or just goes off from plus to minus infinity or vice versa in a straight line. And therefore, to solve the practical problems, we'll, if you like, or if you like from your point of view, the coursework problems, the problem class problems, the exam problems, you won't need this powerful machine, but you need to know it exists and how it works for future reference. So we now reach a completely different type of, yes, Cameron. Here, this is E. This is, thanks very much. I mentioned this at the beginning. My rhos, my E's are horribly similar. This here is the unit vector from the point where there's a current element to the point where I'm doing the measurement. 2 is a current element, denotes the current element. 1 denotes the place where I'm doing the calculation. This is the unit vector along that line. And this is the displacement element along the current element, and this is the square of the distance between the 2 points. Now, this is the moment the people in the front row have been dreading since my last statement. Well, we're going to now, at least you see, I kind of think, well, it would be awful to have come all this way, and especially to come all the way to chemistry. Because to come all this way and at least not push slightly further than what Kieran did last year with the Biot-Savart law, because of course, you know, your maths is better. But more or less the only problem that we can do is still a very high symmetry problem. But it's one that I checked with Kieran's notes. It's one, it's going to really, this one, next step, will particularly annoy the porters in this department. It's one where I'm going to look at, need a space here, a circular loop of wire, and there it is. That is now, so imagine I've got a current going round this loop here. This is the axis of the loop. But remember, this is very different to the problem of the solenoid, in which we had lots of loops all going round and making a cylinder that went on forever. This is just one in the XY plane current carrying loop, or sorry, in the YZ plane. I've done the next calculation. And this will, let's say that this bit here is this local element in this sense. And I want to work out, so that will be the vector from the point where, you see again I'm already running out of hands, and this is soon I'll need some help. I've got a vector, I'm measuring the magnetic field here due to this current going round in this plane, and this is illustrated in figure 27 of the course handout. And again, I say that in the electromagnetism you do need a kind of bit of 3D imagination, and so this is one that I'm going to go through with a kind of demonstration, because a lot of people get confused about this this cross product that we're just about to do. So again, the view graph has disappeared of figure 27, but it's in here somewhere. There it is. Again, I copied this unfortunately out of a book where the displacement element around the circuit was written in a different way. So I've got a current element. The radius of the loop is A. That's a fixed. That is actually the radius. This is a circuit, a circular circuit carrying a current I. And by using the Biot-Savart law directly, I need to be at this very high symmetry point on the axis. As soon as I move to anywhere that's not on the axis of the coil, I need the vector potential. But let's just do it at this point. So, of course, when I'm comparing it with that, I'm going to put this in this plane here. So if you like, to make it, that's my circle. This, of course, is the axis of the coil, and this is the vector from the point where I'm doing the measurement. The point where I'm doing the measurement is a vertical distance x. Again, you're perfectly capable of changing variables. I've now, in this case, got this as the YZ plane, and I've got this as the x-axis. Okay? Could I have a volunteer to hold these two rulers steady for me, please? All you've got to do is hold that. Yes, thank you. So the cross product here, remember, I can go round there. So there's my little current element, yeah? Well, that vector, the whole point of it being a vector is I can displace it in space. I can put this vector here. Let's just hold the ruler there. And the cross product of these two is emphatically not along the x-axis. The cross product's perpendicular to this ruler and this ruler. This ruler represents the current element, and it points like this. But as I go round, we now need to move, let's move round. Yeah. This cross product moves with it. Yeah. It started here, and it goes round. And then let's move round again, maybe to this side. Maybe you need to swap hands. So again, now the cross products that are pointing here. So the cross, as I go round, thanks very much. I hope that's made it clear what this represents, is that as I go round here, this thing, this vector, again, if I displace it, let's say it was like that, it goes round with the current element, it goes round, the cross product traces out, if you like, a cone. Yeah, so it's going to be this dB is a cone. Now, because in the cone, as it traces out a cone, the Y components will always cancel from the different sides of the circuit. The Z components will always cancel from the different sides of the circuit, but the X components are all pointing in this direction, and they add up. So the magnetic field of this coil is specifically along the axis, even though the cross product in the Biot-Savart law is not along the axis. So the cross product in the Biot-Savart law is off axis. But as this element goes round, the cross product goes round, and so in the end, because this now, the top end of it, if you like, what's being represented here is that the top end is tracing out a circle, and all the X components are along the axis. We are finally producing a field. When I do the integral around the whole loop, all the X components add up, and all the Y and Z components cancel out because they're on opposite sides of this circle. So I know immediately that the magnetic field must clearly be of this type. So one thing I'm not going to, of course, bother to do is calculate all these y and z components that I know are going to cancel out in the end. I'm only going to calculate the non-zero x component of the magnetic field. Now, the nice thing is, and again, you know, this I'll actually do this calculation, I think, on the board because, you know, get a bit fed up just following the notes from the from the VLE. We want to keep this, definitely, because this is the formula that we're using. So let's use this board here underneath it. So when I apply the Biot-Savart law, again, I think Biot and Savart were two French scientists who discovered this law in the late 19th century. I mean, I think this law was actually discovered after the unification theory. I'd have to check on that, but I think that's the case. Well, obviously, first of all, the current is just constant round the loop. The same current is flowing, the same scalar current I is flowing for any one of these circuit elements. So clearly, the magnetic field at point 1, where I'm doing the calculation, is obviously going to be given by this integral, ds2 cross E12 over R12 squared. Yeah? Now, again, this is why we need the high symmetry point, is that the distance, although the direction is changing all the time, if I'm on the axis, again, I'll go back to the axis, clearly as this goes around, the distance of this point to any of these current elements is also constant. Yeah, I mean, if I go around here, 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 I go all the way around the circle. I've certainly not changed the distance from the current element to where I'm doing the point of the calculation. Therefore, and now this is where things start to really simplify and why I'm doing a high symmetry point. This integral, of course, could be, excuse me, this is integrated around the circuit. This is clearly, and again, by abbreviation, we know we're calculating the magnetic field from point 1 to 2. It's usually just written as R, and it's a constant, so this one also comes out front. Now you can imagine as soon as I move off the axis, and this isn't true, this integral becomes hard. It's got a cross product, and it's got a cross product in which the direction of this is varying in space and the distance is varying in space. But in this particularly beautiful high symmetry case, this r squared comes out front. And now all I've got under the integral sign is this cross product. Well, again, and I think we don't need to reset up all the rulers, get the front row bouncing up and down. First of all, the magnitude of this is obviously constant. This is a unit vector, yeah? And this is ds2, so its magnitude is just ds2. We've just got to think about the direction. And again, I think it's fair enough if I just take off. We know that the magnitude is ds2. Well, what is the cross product between E12 and ds12? Well, it's the magnitude of E12 times the magnitude of ds2 times the sine of the angle between them. Again, that was our, if you like, definition when we started with the cross product, is that the magnitude is given in this very, very simple way. Now, again, we're not working out the y and the z components. Why bother? We're only working out the x component of this thing. And let's go back to tipping it this way. It seems pretty obvious that this is a right-angled triangle, yeah? And we've got where it's got a radius a. Let's just draw it in here. A radius a. This is r. This is x. This is a right-angled triangle. So sine of phi is equal to a opposite over r, yeah? Where, of course, r squared is a squared plus x squared. So we've got now, this whole thing is just ds2 sine phi. So that's going through it gradually. This is clearly, of course, the magnitude of a unit vector is 1. And this is the magnitude of ds2, is just abbreviated to this. And this is sine phi. And this sine, and again, you see, this is where, again, we precisely got this beautiful high symmetry problem that enables us to simplify. It's as we go round, sine phi is, well, it's just equal to the constant distance a, this is a constant, over the constant distance r. And again, you can imagine if I'm off axis and this isn't true, the integral's becoming horrible. But because that's a constant and that's a constant, sine phi is a constant, so that comes out of the integral sign as well. So next step, the magnetic field at this point, and now remember, I'm just calculating the x component. So, you know, we know that the magnet, you know, if I've got B is equal, which it must be by symmetry to this, well then the magnitude of it, B, is equal to the magnitude of, is equal to its x component. You know, that's just immediately obvious. A 4 pi r squared times the sine of phi, because this one pops out the integral, all I'm left with now is the integral around the circuit. So it looks like a vicious looking law, you know, cross product under an integral sign, but because the distance is constant, because the sine phi is constant in the cross product, and it all comes out, I'm just left with the integral around the circuit. And now we've got, trivially, if I integrate the distance around a circle of radius a, I've got 2 pi a. Yeah, I've solved the problem. Now, exactly, I would, this of course is a solution, but normally this solution is expressed, and of course I can just trivially there, I've got a 4 pi here, yeah, and a 2 pi here, obviously the pi cancels off, so I've got this as mu naught I, yeah, that one, over 2, and now I've got a over r squared sine phi. Now the usual way to express the answer in this problem is to say, well, of course, just continue this over here. This is my x component of the field is, well, a is over r squared is obviously a over a squared plus x squared, right angled triangle containing a, x and r. This one is, so I can always replace my r squared by a squared over x squared. We've already seen that sine phi, the whole reason we could take sine phi out of the integral, it's a over r. So I can replace my sine phi here by a over r. So this becomes a squared over r cubed. And my bx final, sorry, that might as well just write it now in one line, is equal to mu naught I halves times a squared over a squared plus x squared to the 3 halves power. Yep. I've got an r cubed, which is a squared plus x squared to the 3 halves. And so, again, you know, that is the final answer. So there's one or two things I'd like to say about the answer. So I've gone through that derivation. This is why we've got this result. Now, again, it's always nice to link up with what you've done previously. And I checked with Kieran's notes. And I think with Kieran, you actually did the magnetic field actually in the middle of the circle, which of course is an example of being on the axis of the coil. It's just being on the axis of the coil at x is equal to 0. Yeah. So you better sure as hell get the same answer from what you've done previously. When x is 0, well, of course, that's trivial. That just becomes a cubed, and a squared over a cubed is a. And so you get the strength of the field at the centre of the loop as mu naught I over 2a. Lovely simple result after all this hard work. But also I'd like to point out too that when x is much greater than a, in other words, you know, like I've got a little radius a here, and I calculate the magnetic field at some very large distance x on the axis of the coil, well then that's going to be small, and x squared to the 3/2 is x cubed, and so I get an inverse cube field for the strength at a long distance. Remember, this is an approximation. The accurate, perfectly accurate formula is this one, but you get a 1 over x cubed. And again, we can't do all the history. Oh, it says just coming up for 5.2 there, so I just finished. You can't do all of the history of physics, but actually it was a very important moment, was called the Roland's disk experiment in 1898. And this there were still arguments about magnetism, even 30, 40 years after the Maxwell equations. And one of the arguments was that, well, magnetism seemed to be produced only by metals. Yeah, at that time, it was only currents flowing in metal circuits, usually copper, but it could have been silver or gold, any current carrying conductor, or by bar magnets, which of course are made of iron. And people were still arguing and saying, this is a property of metals, this isn't a fundamental thing. And Roland had the idea, now you've got to do one extra integration to get the magnetic field on the axis of a disk. Because what you do is you build the disk up as a series of concentric circles, and then you integrate of the disk. Yeah? So if you like, I already annoyed the porters here, instead of having a single circuit, we can work that out. Well, of course we can work it out for a different radius A and a different radius A until we fill in the whole disk with lots of concentric circles, and then the total field is done by an integration across the disk, and it still gives you, prove it to yourselves, it still gives you an inverse cube field. So Roland charged up a ceramic disc and spun it very rapidly. And he spun this disc, this was a ceramic material spinning, yeah, there's no metal at all in the system. He charged it up, spun the disc, and measured the magnetic field out along the x-axis, and got exactly the right constant and exactly the right inverse cubic decay. So there's also historic interest in that. Anyway, I think we've run out of time. The chemists are about to boot us out. Enjoy the weekly problems. Of course you'll